everyone. This video covers the topic of the acceleration vector. In a prior lecture, we learned that the velocity vector is the change of the displacement vector over time, and that the displacement vector itself is also a function of time. So I can write this as my velocity vector, which is a function of space, displacement, and time, is defined as my time rate change of my displacement vector, which itself is also a function of time. And so after differentiating displacement with respect to time, we were able to rewrite the velocity vector like this. Where I, j, and k respectively are my unit vectors in the x, y, and z direction, and my u, v, and w are the velocity components in x, y, and z. Let me switch to a different color here so that u is my v component in the x direction, v is my v component in the y direction, and w was my v component in the z direction. And this is the same thing as saying, the change in x with respect to time, the change in y with respect to time, and the change in z with respect to time. Right? So there's three different ways to express the x, y, and z components of the velocity vector. The most common that we're going to see in this class is u, v, and w. But any of these things, they're all mathematically equivalent. Now, we can resolve the acceleration vector, which is going to be the change in velocity vector over time. So my acceleration vector is also going to be a function of space, displacement, and time, and it's going to be my time rate change of my velocity vector, which, remember, is also a function of displacement and time. So remember, because this velocity vector right here is a function of both space and time, I have to apply a chain rule differentiation to derive my acceleration vector. So applying the chain rule differentiation, I can resolve my acceleration vector like this. Now, these terms right here, the dx dt, dy dt, and dz dt, these look awfully familiar, don't they? Right? These are, as defined, my velocity components u, v, and w. So I can simplify this somewhat by substituting in u, v, and w for dx, dy, dz, dt. And so my acceleration vector can be written like this. So I can think about my acceleration vector as being made up of two different parts. The first term, this is what is referred to as the local acceleration. In your high school physics class, this is usually how we've defined acceleration, as the change in velocity with respect to time. So you can see that the local acceleration is a function of time. And if we were applying acceleration analyses to solids, this is all we would need, because every molecule of the solid is moving at the same trajectory at the same rate. But if we're working in a fluid, now every molecule or particle of that fluid can be moving in different directions at different speeds. And so we have to include a secondary piece to understand the acceleration of fluids, which is represented here. So these three terms together are known as the convective acceleration. And what you can see is that these three terms are a function of displacement or space. Right? So we've got the change in velocity with respect to x, y, and z, respectively. So just a little bit of notation that you may see to represent all of the work that we have done here. Instead of having to write this out every single time, sometimes you'll see it written that acceleration is the material derivative, capital D dt, of our velocity vector. So again, the terminology that is used here is the material derivative. And you can see this applied to other properties besides just velocity. In this case, acceleration is the material derivative of velocity. What does material derivative mean? It's all of the work that we've just done in this video leading up to this point. For me personally, this simplifies it a little bit too much, the notation you'll see sometimes. And I want to point out that this D right here is not the displacement vector. It's a capital D, but no vector symbol over the top of it. It's just notation telling us to expand, velocity out throughout space and time. So another type of notation that you might see to represent the acceleration vector, which also gives credence to the fact that it's a material derivative of velocity, is that you might see something that looks like this, where we've got the first term, the change in the velocity vector with respect to time. Sorry, that's a big V there. And then the second part that has the three terms that are a function of space, the convective acceleration, can be wrote using the gradient operator, so v dot del v. So these two notations are exactly the same thing and are meant to just convey all of the work that we did to lead up to this point. So if you see them, just remember that this means that our acceleration vector is a function of velocity, or the time rate change in velocity. The velocity being a function of both space and time, we have to do a chain rule differentiation to reflect changes that can be happening both in time and space that lead us to this two-part acceleration, the local plus the convective acceleration, where the local is a function of time, the convective is the function of space. This material is based on work partially supported by the National Science Foundation. Thank you for supporting this work under Grant 2335802. Great job reaching the end of this video, and please reward yourself with a moment of Zen. I study fluid mechanics because I love water and healthy aquatic ecosystems. Whatever your passion is, I hope that it motivates you to continue your study of fluid mechanics.